Okay, I really like this question. It's a, we need to rank the tensions in these wires. So all of these have different tensions, and we need to rank them. So why is there any tension on these wires in the first place? There's tensions on the wires because these objects are in static equilibrium. All of them are identical. They have some kind of little bar out to the side with some weight. Maybe the bar has a weight too, but the point is the bar is completely consistent. So there's some kind of torque that's consistent in all of these in the clockwise direction caused by these weights. So that is a constant. That has to be balanced by a torque in the counterclockwise direction by these various cables, which implies there's a tension. So, in other words, all of these all of these torques all equal each other. The downward torques are all equal because of the same mass and the same bar, and since they're not being lifted up, all of the counterclockwise torques must be the same. So, remembering the definition of torque as equal to force perpendicular to a lever arm, and the force is caused by these tensions, where are the tensions greatest or least? Well, I've made some indications. Sometimes the ropes are way out here on the end, and there's the full length of this lever arm. We're going to assume the pivot points are always right here on the end. There's pivot points right there. So so out here, any rope that's tied to the very end has the advantage, has the torque advantage of the full length of these bars. Some of the ropes are tied, it looks to me about 3/4 of the way out on the bars, and there's one that's tied halfway out. So if we look at the torque, and notice all the torques have to be equal. All torques are equal because the torques in the clockwise direction are all equal, so the torques in the counterclockwise direction are equal. The only thing that differs is the tension in these wires and these lengths. So notice that these three are all of the same category. They're all perfectly perpendicular already to each other. The only reason they vary is they vary in L. This is L. This is 3/4 L. L. This is 1/2 L. And this is the full L. So if they all have the same torque, this guy has torque is equal to whatever this tension is. I'm going to call this, just to keep track, A, B, C, D, E, F. This guy has tension B, upwards times 3/4 L. This guy has torque equals tension C times 1/2 L. this torque is tension E times L itself. So these guys all have torques that are proportional to L, but if they're going to all be equal, then, well, we'll look into that. Well, actually, no, let's do it right now. If these are all equal, what I can write it down here. Torque, tension B, 3/4 L is equal to tension C, 1/2 L, which is equal to tension E, just L. If all of those are equal to some torque, I can divide everything by L. So I can divide all of these terms by L, and the L just ends up over here. It's just a constant. It's the same as that constant torque. It's something. So this tension E is equal to half of tension C. So it's much easier for a tension to hold up this sign and this weight when it's way out here than it is in here. So the E tension is only half as much as the C tension. And the E tension is only 3/4 as much as the B tension. So we can rank these tensions, these three already. This is the least, E. This is the most, and this is in the middle. So there's weakest, stronger, strongest out of those three. Because it's easier for a wire to hold up a sign way out at the end where the lever arm is longest, producing the same amount of torque as these guys do, using a longer lever arm and a weaker force. This guy uses the shortest lever arm and has to have subsequently the largest force. So we can now rank those three. From, what is it, largest to smallest. So largest is C, next largest is B, next largest is E. All right, let's bring in these other ones. This torque is the same as all the other torques, and it's caused by a force, and remember it's the perpendicular force. That would be the perpendicular portion of this tension here. That's the opposite side, so that's sine of 60 degrees, and the times this tension of A, and that's working at a distance 3/4 L. This one here is this torque. The torque needed to hold this up again is the same thing. It's working at a distance 3/4 the entire length. And here the effective force is the perpendicular force. That's this force perpendicular. This is a force perpendicular. And this is equal to sine of 45. Sine of 45 degrees times the tension in chord D. This one is interesting. It's providing the same amount of torque as all of these other ones. We're just balancing out the same sign and the same post, the same bar. It's at a shallow angle. Only the vertical part of this tension, I'm assuming there's a tension on this string, only the vertical portion of this tension, of tension F, this is tension F, just the vertical portion of it, that's the vertical portion is opposite of 30 degrees, so that is sine of 30 degrees, tension F, working at the full length. So all of these tensions are equal. They all depend on L. You can cross out L as a dependence from all of them. And then you just have these factors depending on where they were placed. There's a halves, 3/4, depending on their location. And then these factors dependent on their angles. Sine 30, sine 45, sine 60. You can substitute those values in, figure out how the relative size of all of these tensions and rank them mathematically, and then you can rank them symbolically using drag and drop on the problem. Just point out it goes from largest to smallest, not smallest to largest.